One of the things we talked about in class today was how you could determine the strength of an acid and then the strength of its conjugate base. So just kind of reviewing, the stronger the acid, the weaker its conjugate base, and the stronger the base, the weaker its conjugate acid. And in both of these situations, when we say weaker, what we mean by that is weaker than water. And that means water acting as either an acid or a base. So, for instance, let's say I've got hydrochloric acid, and I know that that's a strong acid. So, what this tells me is that if I were writing a reaction of that dissolving in water or dissociating in water, I would get the hydronium ion and the chloride ion. And HCl looks most like chloride, or if you remove a hydrogen from HCl, you're going to get the chloride ion. So HCl is your acid, and chloride is your conjugate base. So we know that hydrochloric acid is strong. What that means is that the conjugate base, the chloride ion, is going to be a weaker base than water. So that means that water is more likely to accept a proton than the chloride ion would. Then likewise, the stronger the base, the weaker its conjugate acid. So if we have a strong base, so let's say, oops, sorry, I didn't mean to do that. I'm going to stop. Okay, so sorry about that. There was a bunch of silence that you had to sit through. So if we have a strong base, I'm just going to say hydroxide. And we're putting that with some weak acid, so let's say maybe phosphoric acid. So the base is going to accept a proton from phosphoric acid, and we are going to get water and dihydrogen phosphate. Only one proton, so it's 2 minus. So because we know that the hydroxide ion is strong, this is our base, it's a strong base, so then that means that the conjugate acid, water, would be weak. This was kind of a silly example for me to do since it's supposed to be weaker than water, and it actually is water. But hopefully you get the idea between those two things. Okay, so now what I want to do is look at a chart. This is in your book. It's actually on page 672 in your book, so if you want to reference it later, you can. But this is just showing you a comparison between acids. Strong acids are at the top, weak acids are at the bottom, or negligible acids are at the bottom, and then bases are kind of flipped. So here you've got hydrochloric acid as being a very strong acid. Its conjugate base, which would be the chloride ion, is weaker than water. And here you can see water is right here. Sulfuric acid is a strong acid. Its conjugate base, which is the hydrogen sulfate ion, is a weaker base than water. So then if we go down a little bit and let's look at a weak acid. So let's look at carbonic acid. Its conjugate base, which is hydrogen carbonate, is a stronger base than water. I hope I said that this was a base. I may have said that it was an acid, and if I did, I apologize. So once again, carbonic acid is a weak acid, so that means that its conjugate base is a stronger base than water. We can also do the opposite. We can do the same thing with bases. So let's say I'm looking at a strong base. So I'm going to say, all right, the hydroxide ion is my strong base. So that means that its conjugate acid is weaker than water. If I take a weak base, and you know that ammonia is a weak base, so ammonia's conjugate acid, ammonium, is going to be a stronger acid than water. And if you look at this, then you see here's ammonium and here's water. So that's basically what the table is telling you. I want to mention, we've looked at some reactions where we've just had a proton, H+, or we've just had hydroxide in the reaction, OH-. Those two, H+ and OH-, H+ is the strongest acid that you can have in aqueous solution, and hydroxide is the strongest base that you can have in equilibrium in aqueous solution. Now, if you have a acid or a base that you would say, hey, I think this is a stronger acid than H+, so like hydrochloric acid, you may say, okay, that's a stronger acid than H+. What that means is basically all of your HCl is going to ionize or dissociate completely to produce H+ and Cl-. So we had talked about this with the equilibrium chapter, that essentially HCl is not present, molecular HCl is not present, and all you have in the solution is its ions. So that would mean that H+ or hydronium, if you chose to write the reaction as HCl plus H2O, either proton, H+, or hydronium ion are present. So that's what that means. Now, how do we identify this in a reaction? Oh, I probably ought to mention this, so let me go back and just talk about these last two things. The conjugate, let me get rid of all my drawing, sorry. The conjugate base of a strong acid, so let's go back and talk about HCl again as our strong acid. And as we learned in class on Tuesday, conjugates differ from the regular acid or base by a proton. So HCl and the chloride ion are your conjugate acid-base pair. So HCl would be your acid, and the chloride ion would be your conjugate base. So the conjugate base of a strong acid, so I'm talking about the chloride ion, has negligible acid-base properties in water. What that means is it is a weaker base than water, so we consider it neutral. Likewise, if we're thinking about the conjugate acid of a strong base, so let's talk about our strong base as being, we could do sodium hydroxide. Sodium hydroxide would give us sodium ions and hydroxide ions. Now, I'm not going to add a proton to sodium because that's just not going to happen. They're both positive. So if I want to say that my base is sodium hydroxide, and sodium would be my conjugate acid. Or if I want to say that hydroxide is my base, which would make water the conjugate acid. These have negligible acid-base properties, and so we would call them neutral. So now what I want to look at is, what do we do when we're given a reaction and we want to identify which side of the reaction is stronger, which has the stronger pair. So the first thing we do is we look at the reaction as it's written, and we see what's most similar on both sides. So the first thing here would be hydrogen sulfate and sulfate. So that's a conjugate acid-base pair. Hydrogen sulfate loses a hydrogen, so that makes it an acid, which then makes sulfate the conjugate base. And carbonate gains a proton, so that makes carbonate the base. And hydrogen carbonate is going to be the conjugate acid, because when the reaction is reversed, it's donating a proton. So now I want to decide is to which side is the equilibrium shifted. It's an equilibrium reaction. I see that by the arrow. And I want to know, is the reaction reactant favored? Is it product favored? So to which side does it lie? So what I do is I look at my acid and I ask myself if it's strong or if it's weak. This is weak. So then I know that the conjugate base is a stronger base than water. Carbonate is, this might be good to actually go look at my chart, but carbonate is not one of our strong bases. So then I know that the conjugate acid, hydrogen carbonate, is a stronger acid than water. Both of these are weak. And so then I'll look at these and I'll say, okay, this is a stronger base than water. This is a stronger acid than water. And then I have to decide which way am I going to go. What I would do in that situation is I would go back and I would look at that table. So we're going to go back to that slide. And when I look at this slide, I'm going to get rid of my drawing so you can focus on what I need you to focus on. In this table, we had carbonate and sulfate. So I'm going to circle these. Here's my sulfate. And I think carbonate was a base. I don't remember. I think HSO4 was the acid. Sulfate was the conjugate base. And then bicarbonate was the conjugate acid, and carbonate was the base. So this is what we had in our reaction. So if I look at this, looking at my table, I'm looking at the two bases to see which is stronger. Now for my bases, closer to the bottom is stronger, closer to the top is weaker. So I see that carbonate is a stronger base, and I see that hydrogen sulfate is a stronger acid. So if I go back to this pair, this acid-base pair right here, hydrogen sulfate and carbonate, these two are stronger than this pair. So I know that the reaction is going to be shifted toward the right. So that would mean that we have an equilibrium constant that is greater than 1 because it is product favored. Okay, I'm going to do the same thing with this reaction. My hydrogen phosphate looks most like dihydrogen phosphate. Hydrogen phosphate is gaining a proton. Proton acceptors are bases. So that makes dihydrogen phosphate a conjugate acid. Water is donating the proton. So water is our acid. That makes the hydroxide ion our conjugate base. And we know that hydroxide represents a base anyway. Okay, if you remember what we talked about, or I mentioned a couple slides ago, I talked about if you see hydronium, if you see the proton, if you see hydroxide, you need to consider that strong. And then following the rules that we just learned, hydrogen phosphate as a base is a weak base, so that means that the conjugate acid is a stronger acid than water. Okay, so if we look at what we have right here, on the product side, we have a strong base. We have an acid that's stronger than water. On the reactant side, we have a weak base and water, so we know that the product side is stronger. Oh, that's a better muscle. So we know that the reaction is going to be shifted more or pushed more to the reactant side, so we have an equilibrium constant that is less than 1. One more example if you need it. If you don't need it, you can skip and listen to the next video. Ammonium looks the most like ammonia. Ammonium is donating a proton. That makes it an acid, so ammonia is our conjugate base. Hydroxide looks most like water. Hydroxide is accepting a proton. That makes it a base, so water is the conjugate acid. If you think about the rules that we just learned, hydroxide we know is a strong base. Ammonium is a weak acid, so its conjugate base is a stronger base than water. Now we've got water here. If I try to look at these two bases, clearly hydroxide is stronger than ammonium because we know hydroxide is a strong base. I'm sorry, this is ammonia, and ammonia is a weak base. If I look at this in the reverse direction, ammonia is a weak base, so that means that ammonium is a stronger acid than water because this works both ways. And that just means it's more likely to donate a proton than water is. So if I look at my pairs, my reactant pair is stronger than my product pair. So the reaction is going to be pushed or shifted to the right, which means it's product favored. Our equilibrium constant is greater than 1. So one thing I mentioned on this slide was that when something is a stronger acid than water, that means that that acid is more likely to donate a proton than water would be. If something is a stronger base than water, that means it's more likely to accept a proton than water is to accept a proton. This is pretty much all you need to know about relative acid strengths of acids and bases. I'm going to do another video that's going to talk about how we express this quantitatively And you may want to watch that tonight before class tomorrow.